The West prides itself on technological dominance, yet when it comes to fundamental construction, we often build weaker, slower, and less resilient structures than the rest of the world. Why do we consistently ignore proven, superior engineering methods from other cultures? This is the core mega defect of engineering hubris. Here are the 5 global engineering secrets the West is failing to adopt. 1. Japan's base isolation tech. 2. Ancient Rome's self-healing concrete. 3. Thin joint masonry. 4. China's modular speed. And 5. Japan's flexible timber joinery. Let's expose these global secrets. These secrets prove that true resilience is built from the foundation up, and that same principle applies to your digital life. You wouldn't ignore a structural flaw in your home, so why ignore vulnerabilities online? That's why securing your digital environment is an essential defense. And for that protection, I trust NordVPN. NordVPN encrypts your connection, building an impenetrable tunnel that shields your online activities from hackers, snoops, and data brokers. It's your defense against digital system failure. Beyond robust security, NordVPN gives you the freedom to bypass geo-restrictions, granting you private access to global content. With thousands of high-speed servers and a strict no-logs policy, NordVPN ensures your digital life remains secure and under your control. Don't let hidden vulnerabilities compromise your online world. Secure your digital self today. Go to and use code MEGADEFECT for up to 73% off, plus 3 extra months. Our first secret, Japan's base isolation technology, is a life-saving solution the West has yet to fully adopt for widespread residential and commercial use. This ingenious system involves placing buildings on large, flexible bearings, often made of layers of rubber and steel or sliding friction pendulum systems that act like massive shock absorbers. When an earthquake hits, the ground beneath the building moves violently, but the base isolation system actively decouples the structure from the ground motion. The building essentially floats on these isolators, dramatically reducing the seismic forces transmitted into the superstructure. This not only prevents catastrophic collapse, but also significantly minimizes internal damage, keeping buildings functional immediately after even severe quakes. In highly seismic Japan, thousands of buildings, from high-rises to crucial infrastructure and even individual homes, routinely utilize base isolation. In contrast, in the earthquake-prone United States, there are only around 100 such buildings, mostly reserved for essential, high-value structures like hospitals, emergency response centers, or critical data facilities. This disparity exists partly because the Japanese government has a streamlined, accredited process for approval and design, along with substantial public awareness and investment. In contrast, the U.S. requires expensive, project-by-project testing and certification, often paid for by the individual owner, making it cost-prohibitive for most. The result is that a technology proven to save structures from damage and lives from peril remains largely inaccessible to the average Western homeowner or commercial developer, a critical mega-defect in our approach to natural disaster resilience. Next, we travel back 2 millennia for ancient Roman self-healing concrete. While modern reinforced concrete structures are designed with a lifespan of 50 to 100 years before requiring extensive repair, iconic Roman structures like the Pantheon, the Colosseum, and countless aqueducts have endured for millennia, often under harsh conditions, showcasing remarkable durability. The secret lies in the unique mix of local volcanic ash, pozzolana, quicklime, and seawater. For centuries, engineers were baffled by its longevity. Recent research has revealed that this ancient mixture contains microcracks filled with lime clasts and other reactive compounds. When cracks form due to stress and water infiltrates, it reacts with these lime particles to create calcium carbonate crystals that essentially regrow within the crack, autonomously sealing it. Furthermore, when exposed to seawater, this unique concrete forms rare aluminum tobermorite crystals, which further strengthen and reinforce the structure over time, allowing it to thrive in marine environments where modern concrete rapidly degrades. The Roman engineers weren't just building, they were creating living, evolving structures. The West is just now attempting to replicate this lost technology, experimenting with bioconcrete and self-healing polymers, highlighting a fundamental megadefect in modern material science that has prioritized high initial compressive strength and rapid construction over millennia-scale durability, sustainability, and true resilience. Our third secret is thin joint masonry, a superior construction technique widely used across Europe, parts of Asia, and other advanced construction markets, yet rarely seen in North America. This method uses a high-strength, quick-setting adhesive mortar that is significantly thinner, often just 1 to 3 millimeters thick, between precision-engineered concrete blocks. This contrasts sharply with traditional Western block laying, which uses thick, imprecise mortar beds, typically 10 to 15 millimeters. The advantages of thin joint masonry are numerous and significant. Firstly, it dramatically speeds up the wall building process by up to 50% because less mortar means less drying time and more efficient material handling. Secondly, it results in much stronger, more structurally rigid walls with superior load-bearing capacity and reduced shrinkage. Thirdly, and critically, the thinner mortar joints create a much better thermal barrier, significantly improving the wall's insulation properties and reducing thermal bridging, leading to more energy-efficient buildings. Because the adhesive sets quickly and consistently, interior finishing work can begin much sooner, accelerating the entire construction timeline and reducing overall project costs. By using less mortar, achieving better thermal performance, and gaining superior structural integrity, this technique offers a more durable, energy-efficient, and faster final product than the traditional thick mortar block laying common in many Western countries. Its limited adoption in the West is often attributed to entrenched traditional practices, a lack of specialized training, and a fragmented supply chain for the precision blocks required. Secret number 4 is the highly advanced Chinese prefabrication and modular construction, which prioritizes unprecedented speed, precision, and efficiency over the traditional chaos of on-site building. This method involves constructing entire three-dimensional building sections, complete with pre-installed wiring, plumbing, insulation, windows, and even interior finishes, off-site in massive climate-controlled factories. These complete modules are then transported to the construction site and rapidly assembled by cranes, often in a matter of days or weeks for multi-story structures. This approach dramatically cuts construction times by up to 50 to 70%, reduces material waste by over 80%, and significantly improves quality control by eliminating weather delays and inconsistencies in on-site craftsmanship. China has demonstrated the ability to assemble a 57-story skyscraper in just 19 working days, and residential houses in mere minutes. While the West uses some modular techniques, China's national policy, massive investment in specialized factories, and commitment to industrialized construction have allowed them to achieve an unprecedented level of speed, efficiency, and scale that traditional Western residential and commercial builders simply refuse to adopt. This reluctance is due to a combination of factors: fragmented construction industries, complex and localized regulatory barriers, union resistance to factory labor, and a general cultural preference for traditional, less efficient on-site methods. It represents a massive lost opportunity for addressing housing shortages and reducing construction costs in the West. Our final secret returns to Japan for traditional timber joinery. While Western light frame construction relies heavily on rigid steel plates, nails, screws, and other metal fasteners to hold timber structures together, traditional Japanese wood construction uses incredibly complex, interlocking wood-on-wood joints. These intricate designs, often resembling three-dimensional puzzles, create a structure that is designed not to be rigidly fixed, but rather to flex, shift, and give during seismic events and high winds. This flexibility allows the structure to dissipate energy rather than rigidly resisting it and breaking. When an earthquake shakes, the joints are designed to move slightly, absorbing the energy and preventing catastrophic structural failure. This philosophy of adaptive resilience is the opposite of the rigid connection philosophy prevalent in much of North America. Furthermore, these joints require no metal fasteners, making the structures incredibly durable and easier to disassemble for repair or relocation, extending their lifespan for centuries. When combined with modern techniques, this ancient wisdom proves that a structure built to move can be infinitely more resilient and long-lasting than one built to stand perfectly still. This philosophy offers massive insights for areas dealing with seismic activity or extreme weather, showing that sometimes the oldest secrets are the strongest, and that a deep understanding of materials can create engineering far superior to our modern methods. These 5 examples prove that the rest of the world holds vast libraries of engineering knowledge, both ancient and modern, that the West, constrained by outdated codes, segmented industries, a lack of investment in innovation, and simple arrogance, refuses to fully adopt. We continue to build weaker, slower, and less resilient structures because we prioritize short-term costs, comfortable familiarity, and entrenched practices over genuine, long-term durability and efficiency. The failure to adopt these global secrets is not a technological one. It is a systemic mega-defect born from a failure of humility and a stubborn refusal to learn from the world's best. It's a choice that costs us in safety, sustainability, and economic efficiency. Which of these 5 global engineering secrets do you think the West needs to adopt immediately? What other infamous engineering blunders have we ignored? Share your thoughts and insights below. If this investigation into global flaws resonated, hit that like button, share this video, and make sure to subscribe to Mega Defect for more deep dives into the systems that fail us.